Alrighty. Wow, this is a lot. A2's got a lot of equations here. These are our friction equations, right? Notice that this one's static friction, and this one is the dynamic or kinetic friction, right? Nobody calls it dynamic, but IB does, right? Notice that this one's inequality. So if it is sliding, we're going to say that the force is exactly equal to this. And remember, this is opposite the direction of slide, okay? This one is, it's not moving. It's sitting still, right? V is 0. And this gives us, this is like a limit. It's less than or equal to this maximum thing, right? And so I did a demo, right? Remember the demo was I exerted the force on this thing over time, right? And the force, I just sort of went up. I just increased the force and it went up, and then it dropped down almost instantly once it broke free of the surface, and then it slid along here, more or less. So this is our dynamic force, right? Foot, right? And then this is the maximum static. Notice that when I exerted less than the maximum, of course, it just exerted that force back on me. And I increased it, it broke free. So this thing just simply answers, does it move or not, right? Okay. This guy down here, this is our Hooke's law, okay? Now, if IB is being consistent, this really should be the Hooke's force is minus K times the change in X. So just remember that this is how much you've stretched the spring. So if the spring is this long and then you stretch it, right? This is our change in X, right? And notice that we stretched it to the right, but the spring is going to exert a force to the left, and that's why there's a minus sign there, right? Okay. Technically, I never really use it, but when you set up calculus equations, then there it is, right? This is your Stokes force, right? So if you have a small particle falling through a fluid, here's our fluid. Right? You imagine this, and this thing's moving down through the fluid, right? This is the force that is exerted upward on it. So as it moves down, it's like a friction force, right? It opposes the direction that you're moving it through the fluid, right? This is the viscosity, right? That's the radius of it, and that's the speed it's going through there. And this is not a bullet traveling through the air. This is, a small particle moving at very slow speeds. Okay. This guy here, this is the buoyant force. Okay. So if I have a liquid here, and I've got it's always a beaker or something, right? If I have some object in here, doesn't matter what shape it is, right? Okay. The density of the fluid, the volume that the object displaces. So if it's entirely submerged, that would be the same as the volume of the object, right? Volume displaced. And then G, right? And what it ends up being is it's the weight of the displaced water. Sorry, displaced fluid. Water, fluid, okay? The weight of the displaced fluid, right? You also, by the way, if something floats, it's going to displace a mass equal to its own mass. I mean, that works, right? Okay. Now, oftentimes you're going to be asked, well, what is the net force on this thing, right? Okay. And what it ends up being, right, the net force ends up being the difference between the weight of the object and the buoyant force, right? And so it'll be the density of the fluid. Sorry, it'll be the volume times gravity times the density of the object minus the density of the fluid, right? So that's a shortcut that you can do, and it just comes from the fact that the mass or the force of gravity on the object, the weight of the object is rho times of the object, right? Times the volume of the object times g if it's immersed, right? And the buoyant force is the density of the fluid, the volume, right, and gravity. Okay, so just remember that this is a handy thing, right, to find it's the difference in that. So understand if the object has the same density as the fluid, there's going to be no net force, right? Which is kind of fun, right? You can find like waterlogged tree trunks underwater that are essentially neutrally buoyant, and you can move them around. I used to do that when I was a counselor in the boundary waters. This is just the force of gravity, right? on an object. This is, let's switch gears here. So now we're getting into fun stuff, right? So this is momentum. And remember, this is conserved. So if you add up the total momentum before, total momentum after, it'll be the same, right? And it's, of course, keep track of the pluses and minuses for that, right? Apparently, they're using J for impulse, right? Okay, so this is impulse. And remember that you can also, there's a whole series of problems you can solve by saying that the change in momentum is equal to the impulse, right? And so you can say mass change in velocity is force times time, right? We solved like rocket problems and stuff with that, right? Okay. And then this is our sort of our final momentum one. This is actually how Newton stated the second law, right? It was that force is the time rate change of momentum. Okay. And we can actually, if we sort of rearrange this, right, force is change in momentum over time. Right? If we rearrange that and go force times change in time is equal to the change in momentum. Well, change in momentum will be mass change in lots, and you can get it from there too, right? So really, it's just F equals ma, right? Okay, and then the final thing is these are our centripetal accelerations. So if we're moving in a circle, right, and we have a tangential velocity or we have a period of rotation, the time it takes to go around once. This is the acceleration. Remember that centripetal accelerations are toward the center. They love to ask conceptual questions about this, right? That we're changing our rate of our acceleration is perpendicular to the velocity, and so therefore the speed isn't changing. It's just simply the direction that's changing. Okay, this one is velocity squared over r. This is angular velocity, right? Okay, so I remember angular velocity is 2 pi over t, and of course if you just substitute 2 pi over t in for omega, you get this one, right? So these equations are just the same thing. This has got different parameters, but there it is, right? Okay, and then this one is fun, and it's new, okay, in this data packet from the old one, right? So this is just saying if you know the period, it's just basically your speed. If you're moving at a constant speed, it's the circumference divided by the time it takes to go around, right? That's obvious. But it's also equal to your angular velocity, which is 2 pi over t, right, times r, right? So angular velocity times r. So this is the one tangential relationship that they give you. The velocity at the edge of a wheel is omega r. The other ones are the same though, right? So our displacement is the angle times r, right? And then these of course are in radians, right? True angles, right? So at the edge, right, if we know the angle the wheel goes through, multiply it by r. That's just the definition of the radian, right? Angle is the arc length along the edge over the radius. Okay, and then the acceleration, the tangential acceleration, is the angular acceleration times r. And I don't know, I don't think they have anything besides this guy in the data pack. We'll see. Okay, and I think that's it. There they are.